Hello, I hope you are having a good day. Today we'll be looking at our paper. Starting off, the paper was using stainless steel 3D printed wicks. The paper acknowledged that heat pipes are becoming a very common practice in thermal engineering. Metal printing can be cheaper and a faster method to making wicks. The paper mainly explored the benefits of fabricating wicks. Their testing was purely experimental and all values were gathered that way. The parts were fabricated using a metal 3D printer, stainless steel material. They had three parts with different porosities. The system they used to test to gather data was a loop heat pipe system. They measured the wicks for three components for porosity, conductivity, and thermal resistance. The results they found is that 3D printed wicks are viable and can replace standard wicks. They performed well and can surpass the porosity limits that regular wicks have.
This week, CFD update tabulated different materials for the loop heat pipe that's going to be used for the different boundary conditions. I additionally made the geometry in 3D and SolidWorks. The total fluid volume is 15% less than the paper said there should be, but there's just some inconsistencies, so I think I'm going to roll with it. I'm going to keep the mixture between condensed and uncondensed fluid the same, see what the simulation results look like. Additionally, selecting a solver model, going to go with volume of fluid. This because the primary flow regime is slug flow. And additionally, VOF was used in a few different papers with loop heat pipes to back it up. And our paper specifically takes a look at the position of these interfaces to kind of compare the different porosities. So that's very important to look at. Additionally, for evaporation condensation, I'm going to use the interfacial heat flux model. This balances conductive heat fluxes at the interface. This one's built into ANSYS Fluent. I found a few different papers for loop heat pipes that use UDF to achieve a very similar thing. So I think we're going to compare the results, see how they go. I might do a few smaller benchmarks. And then finally, if looking at the wick, instead of doing a pore scale simulation, my computer probably can't handle it. I'm just going to use the porous media zone in Fluent. This has two coefficients derived from the Kozeny-Kármán equation. I found a paper deriving that specifically for 3D printed wicks and its applicability to actual experimental results. So I'm going to use that and see what our results get next week.
So regarding the coding portion this week, I was able to define three different parameters regarding the wick. First, it was the porosity. Now, the porosity in the study was determined by taking the actual mass of each individual printed wick and going about it that way. However, due to our limited resources to compromise, Caitlin created this individual component of the structural cylinder you see here to the left. Now, I took this structural component and redimensioned it to each sample size, and I placed it in a unit cell to kind of determine the amount of volume that this individual component took, and I was able to kind of go about it that way to find the porosity. So looking back at the code, here's all the different dimensions and variables I used to get to my porosity value. Next, I found the effective thermal conductivity, which involves the evaporation efficiency and heat leak. I simply here took the conductivity of the working fluid, which is water, and the structural material, which is stainless steel, and kind of plugged it into this equation here at the bottom and got my values from there. And lastly, I got the permeability values by taking the pore diameters. These values were given by the study, and I took these values and kind of plugged it into this equation here at the bottom, and I was able to get the permeability values that way. Here, lastly, kind of just comparing the results, I do have about like a 20-ish% difference, but that's simply due to the fact that each of these values depend on the porosity value, and my porosity value is differs from the study. However, I am happy due to the fact that they do have the right order of magnitude and are trending towards the right direction. So at least I have some working numbers to work with. And that was pretty much it for me this week.
Finally, moving on to the financial part. We will be considering a factory that opened up in Pomona. This means we have to look at property values and locations that are selling property. We have to consider the 3D printer and the material cost. Material can cost from $129 to up to $1,000. And this is based on which 3D printer they are on. 3D printers have a range of $2,000 to $50,000. The higher the price, the higher end printer it is, and this could mean better print quality. We would maybe want a higher end printer to look at to see if it could print as tiny as we want. Our parts, the porosity of our parts are in micrometers, and we need to be very accurate. We'll be looking at the time it would take to fabricate a part, time until we break even, and we will make a comparison to buying a wick from other companies in the area to see which is a competitive price and to see how long they would require to mass produce parts. We will also look at if it'd be viable to buy one printer or multiple printers. Thank you. I hope you have a good rest of your day.